All right, I'm starting the recording. Happy Thursday, everybody. How many days to the election? 18 days to the federal election day. And the election day is on a Tuesday, right? November 3rd? Tuesday, November 3rd. Let me stop sharing this so I can look at the gallery of your beautiful blank tiles. Let me ask you all a question. How many of you, so indicate with a thumbs up reaction like this. How many of you have already submitted your ballot to vote in the federal election? Does anybody? Brisa, Haley, Juan, anybody else? Ashley? I have. I did it the other day. And I checked to make sure, oops, I'm applauding myself. That's kind of stuck up. I checked to make sure that the county received my ballot, and they did. I didn't turn it into a fake drop box by accident. All right, how many here will have voted by November 3rd, will have mailed in a ballot by November 3rd? Who else? Sergio, excellent. Alexander, great. Jericho, great. With the questions about the Postal Service, I would suggest dropping it off at a Dropbox if you can figure out where they are. They're all over the place. Bring it to an official county Dropbox if you can. Nobody knows about these unofficial GOP drop boxes, so use them at your own risk. How many people are going to vote in person on November 3rd? Is anybody going to vote in person? Nobody? Has anybody
My
volunteered?
brother definitely is, because he's going to need to do a provisional ballot because somehow he didn't get his one.
That's a pain. I had to do that 2 years ago. I had to do that in the primary, the presidential primary. The problem with provisional ballots is they get counted last, I think, but they'll get counted. So I'm trying to ascertain how many people are voting and what you're doing, because I just want to let you know that if something comes up on election day that you have to miss class because you're going to the polls, or you're helping other people go to the polls, or you're just doing something to help more people vote, let me know. I will celebrate you. There's no need to move your schedule around to make class. Okay. Tuesday is very important. There are some people that want us to cancel all classes on Tuesday, and I'm not quite there, since so many of you have voted by mail, and it looks like none of you are going to go and vote in person. But if I missed somebody, just know that it's okay for you to miss class on Tuesday. All right, because you're voting. Just let me know that's why you're gone. Okay. All right. So I had all these plans to start a serious pivot into statistics today, but in conversation with people, people asked that I do more examples of using these probability distributions. Is that cool with people today that I do that? I spent some time talking about probability distributions.
Sounds reasonable.
And some people said, please do some more examples before you give us homework on it. So I'm prepared to do a bunch of examples to show you how you can look at like a word problem and figure out what probability distribution to use to answer the question posed in the word problem. And then once I do that, I'll pivot into the new Navidi textbook, and we'll start talking through chapter 1. And I was looking at chapter 1, and I had overlooked this when we met on Tuesday, but a lot of stuff in chapter 1 is new to us, so it's not such a quick read as I thought it would be. When you get into plots and things, that we can go over that very quickly, because we've talked about that a bunch. But the stuff in the first couple sections about the differences between populations and samples and sources of variation, that's really, really important to us. So we'll take our time working through that and talking through that. Yeah. And as we're talking about Navidi, I also want to point out that Navidi has some chapters. I don't know what chapter number it is. I didn't write that down. But there's some chapters in the Navidi textbook on probability distributions. So it looks like that's a good source to read up about the Bernoulli distribution function, the binomial distribution function, the Poisson, and it'll also talk about the normal distribution and the exponential distribution. And it's got some others in there too. So flip through that text, skim through those sections to see what Navidi has to say about those distributions. And so that'll be good background too. But today I'm going to do some examples. Let me share my iPad with you as I get set up for today. You can do it. Okay. I already did that. And I'll clean up the other stuff later. All right. So we're, what day? October 15th. So before I get going, let me tell you that I'm going to refer to R today. And I have right over here my R Studio all set up to show you some commands and run some commands. So I recommend that you have R opened up as well, so you can duplicate what I do, and you'll have a record in your R history of the stuff we talked about today. And so it's easy for you to get at, easier than just going back and looking at your notes or going back and watching the screencast of our lecture. Okay. So what I want to do is I want to talk about the Poisson distribution and the binomial distribution. There are two very different distributions. Oops. I want to talk to you about how you can use each of them. And I talked about a relationship between the binomial and the Poisson that's important. And I'll show you when you can use that as well. But let's start doing some examples with the binomial. And yeah, so cancer. Let's talk about cancer. Nobody's favorite subject. And specifically, I want to talk about childhood leukemia. And the controversy about childhood leukemia. So it's generally thought that cancers are not a contagious disease. They're not like COVID-19. They can't spread from person to person. But there's some question about childhood leukemia or controversy. Some people think childhood leukemia can be spread person to person, and some people believe it can't. Generally, a cancer is caused by an overexposure to radiation. Or some other carcinogen. So to think that there's a type of cancer that can be spread from person to person is kind of terrifying. And it makes it even more awful that it happens in kids. But let's talk about how statistics is used to shed some light on this controversy. So the evidence that childhood leukemia could be spread from person to person is in cancer clusters. Cancer clusters in regions of the United States where there's no known source of radiation. So I want to talk about one particular cancer cluster that's well documented in the literature, and show how we can use some probability to shed some light on this controversy. So in a 3rd year period between 1956 and 1961, okay, so 5 1/3 years, physicians in Niles, Illinois, oh, come on. Which is a suburb of Chicago, reported 8 cases of childhood leukemia. And I'm going to, abbreviate that as Luke. So childhood leukemia is happens in a child or an individual who's 15 years old or younger. So this was a lot of cases of childhood leukemia for this suburban town. In Niles, there were 7,076 individuals of age 15 or younger. Okay. So one of the reasons that we know that this number of 8 out of 7,076 is kind of odd is that if you look at the neighboring Cook County, and that's the county that includes Chicago, Cook County had 1,152,695 children who were 15 years old or younger. And 286 cases of childhood leukemia. During the same time period. Okay. So Cook County is big. There's lots of people there, a lot of area. So let's just compute the proportion or the frequency of childhood leukemia amongst the children in Cook County. So you compute this ratio, and you get a number that's about 0.000248142. Okay. So this would be the likelihood of a child having childhood leukemia. Okay. Now we can convert this to how many cases per 100,000 individuals, and then we get 24.8 cases per 100,000 children. So this is a standard epidemiological way of measuring the prevalence of a disease. If you've been listening to reports about COVID-19, you know this per 100,000 is a standard way things are reported. Okay. So we want to understand what's happening in Niles, Illinois. Is this really a cancer cluster? Is this really unusual for 8 kids to have childhood leukemia in this 5 1/3 year period? Out of this number of kids. So let's take Cook County and assume that this is normal. Assume this is, this would be, all right, a normal situation. That is, on a normal day, in a normal place, this would be the probability any one kid got childhood leukemia. So let's calculate the probability. So what's the probability that 8 or more kids in a population of 7,076 get childhood leukemia? That's what we want to calculate. If the probability is big, then we would conclude that what's happening in Niles is not unusual. If the probability is small, then we would conclude that what's happening in Niles is unusual. Okay, and if the probability is somewhere in between, then we're like, oh, we don't know. We can't really say. So if we think of, how do we do this? How do we calculate this probability? Well, we're going to look at this as a binomial binomial probability distribution. And the idea is that if we think of X as a Bernoulli trial where it's pick a kid and ask, does the kid have childhood leukemia? Okay. And P is the probability of yes. So that's the success in the Bernoulli trial. And so we're going to take that Cook County probability, which is 0.002 481142, as the probability of success in this Bernoulli trial. And then how many Bernoulli trials are we going to run? Well, we're going to run 7,076 Bernoulli trials. So that experiment, that random event, Y, is going to be a binomial random variable. And so this little tilde is a way of saying our random variable is distributed like and so now I'm writing a binomial random variable with n equals 70 or 7,076, and P being, and I'm not going to copy this again, I'm just going to put that there, P being that probability. And we want to know what's the probability that in the situation of Niles, Illinois, what's the probability that we have 8 or more kids with childhood leukemia? All right. So just to be clear, the problem statement has now been restated in terms of a probability distribution. Okay, so let's remember for a binomial, the probability that a binomial has k. So if you got a binomial experiment, how many times? What's the probability you have k successes? Like in this case, we pick k kids, and they have childhood leukemia, or k of the kids have childhood leukemia. Well, this is given by, in our case, n choose k times p to the k times 1 minus p to the 7,076 minus k. So we'll use this formula, the probability mass function formula for the binomial to calculate this. Yeah, but what is this? Okay. So this, we need our y's to be bigger than k. So this is going to be a summation as our k starts at 8 and goes up as far as it can go to 7,076. So I'm just not going to write that binomial expression down. So this is what we want to calculate. Okay, everybody with me? All right. So this is a summation that has over 7,000 summands. So nobody in their right mind would do this by hand. So let me show you how to do it with R. So with R, what I'm going to do is I'm going to start out by defining a variable. I'll call it V. Let me do this in black. And I type the assignment symbol. And it's going to be the vector from 8 to 7,076. So you should recognize this as being the vector that goes 8, 9, 10, 11, all the way up to that. And then what I'm going to do is that I'm going to use the fact that this right here, I can write this. This is computed by R by using the function binom. I think that's what it is. We'll double check it. Binom, and in this case, k, comma, 70, 76, comma, and then we put in the p, 0.000248. So this is the command that we're going to use. So back up here where I'm writing my R code, we're going to add up all of these binomial values. So I'm going to say we want the sum of D binom over V. So here I'm putting in all these values at the same time by just plugging in V. V, comma, 7076, comma, 0.0002481142, parentheses, parentheses. Okay, so let's see if R likes that. So I'm gonna switch. Can you all still hear me?
Yep.
Yeah.
Can you hear me?
We can hear you fine.
Me. Okay, I just can't hear myself. I don't know that I can hear you, but let's. Oh, I see. Sorry, I'm having some technical challenges here. I can't hear myself, so I think I've been muted. And I can't get up. Okay, I think I'm back. So I'm going to go to R, new share, R. So my vector, these are the indices of my summands. And I want to just double check that the command for computing these binomial probabilities is dbinom. So I typed in a question mark. I'll hit return. And you see down here in the bottom right corner is the help system. And it shows me here that indeed these probabilities are computed with these commands. We haven't talked about any of these other commands here. Maybe they'll come up later, but this is definitely the one that I want. Okay. Does it tell me anything down here? D binom gives the density. Yeah, and that's what we want, the density. So we're going to type sum of d binom of v out of 7076 with probability 0.002481142. Close parentheses, close parentheses. And I hit return, and I get that number. 0.000475 or 477. So that's the probability that or Niles, we'd expect that's the probability we'd expect to see a cluster of 8 or more kids with childhood leukemia. So this is evidence that that cluster is weird. That cluster is not expected, right? 0.04% chance of a cluster like that occurring if the situation in Cook County is normal. So that's how we use that probability. Oop. So this is 0.00047544. What was it? Oh, 476 8672. So a reasonable person would look at this and say, the cancer cluster in Niles is unusual. There must be something causing it.
There are a lot of cities the size of Niles, aren't there?
Uh-huh. And so what I hear you saying, Patrick, is that if you took 1,000 cities the size of Niles, you'd expect 4 of them to have clusters of 8 or larger, according to this calculation. And that's absolutely right. So somebody who's skeptical about the idea of the contagious nature of leukemia would say, if you flip a coin a ton of times, you're going to get long runs that you wouldn't expect, that you would think have low probability. But we know from studying statistics that just because they occur somewhere, or just because it's rare for them to occur in a particular place, it doesn't mean it's rare for it to occur somewhere. And maybe Niles is just the somewhere. Okay. So our use of probability here doesn't put the controversy to rest. It keeps the controversy going. Because it says on the one hand, yeah, the probability is really rare, but on the other hand, maybe we need to know more about what's happening. Maybe it's not so unusual to see clusters somewhere, right? So it keeps the question going, right? If we had done this calculation and found out that the sum of our binomials was like 0.3, then we'd say, oh yeah, this is not a big deal. This is not rare, right? We expect something like this to happen somewhere. And so that would put the controversy to bed, at least about Niles, Illinois. But here, it keeps the controversy alive. But the important point here is that this is one example of how we can use a binomial distribution to address a question like this, to see if something weird is happening. So now let's suppose something slightly different. Let's suppose Y, which was the number of, what do we say, the number of childhood leukemia cases in a town of 7,076. Suppose y is modeled by a Poisson random variable, where lambda, which would be n times p, and so our case, that'd be 7076 times 0.000248 and some other stuff. If you do this product, you get 1.75. So what would this random variable say? And last time I talked about how Poissons and the binomial random variable, they approximate one another when n times p is a moderate amount, but n is really big. So, here, is that really big? Well, it's kind of big. That's definitely small, and that's definitely moderate. So it doesn't hurt to see what a Poisson random variable would say. So if we want to calculate what's the probability if we have more than 8 cases, well, this would be the sum as k goes from 8, in this case, to infinity, right? Because a Poisson distribution has an infinite sample space. Oops. So that's how we would calculate this probability. Now, computers don't generally like to calculate infinite things, and so you can use this trick and use the complement event. So this here is the probability that y, oops, I did another typo here. This is the probability that y is less than or equal to 7. So between y less than or equal to 7 and y greater than or equal to 8, you get the whole sample space. And so you can use this complementary idea, complementary probabilities. And then here with R, you can use the density probability mass function for the Poisson random variable. And its syntax is k comma 1.75. So here we'd want to put, say, let k be 0 to 7. So let's look to see what that gives us in R. See how it compares to the probability that the binomial gave us. So let's calculate 1 minus the sum of d Poisson, where our k is going from 0 to 7 and our lambda is 1.75. So notice here, when I did the example with the binomial, I used a separate variable to set up the indexes or the indices. So my k was going from 8 to 76. Here I'm skipping that step. I'm putting that vector right in there, and that'll work out just fine. And look at that. Look at how that probability compares to the probability we computed before. That's pretty close. So it appears that an exponential is a decent way to approximate this binomial in this case. Okay. So let's go back. Oh, and here we go. So this is approximately equal to what did we get? 0.000468172. So you're going to ask me, Miller, you're just showing me 2 different ways to do this, one with a binomial random variable and one with a Poisson random variable. How do I know the difference? How do I know which one to use? And that's a great question. That's exactly the question I'd be asking if I were a student. And so my answer to you is this. You have this question. And if you can phrase the question in terms of a Bernoulli trial, which would lead you to the binomial trial, sometimes you can just jump right to here. That's fine. This is just helping us see with clarity what the Bernoulli trials are in the binomial expression of the binomial random variable, the binomial distribution. If you can do these, then I would argue that using the binomial distribution is better. It's more accurate. It's more fitting to the process that's being described. So go for that. On the other hand, and also more evidence for that is to get our lambda for this Poisson, we relied on knowing what that n and that p were. I guess you could say in the problem, we know n is 7076, and we can calculate this p, this probability, pretty easily. And I could jump right to that, and that's a fair point too. But if it's obvious to you that it's a binomial, it looks like it's a binomial, use the binomial distribution. Okay, and sometimes it might be more natural to jump straight to the Poisson, and I'll show you an example of that today too. Okay. Somebody want to make a comment? I thought I heard somebody turn on their mic.
Where did you get? You just computed 1.751. You had to round to get that, right?
Yeah, I'm sure you have to round. So
okay, because I was following along, and without rounding, I got a more accurate result. So I was a bit confused.
Well, that would stand to reason.
Okay, that makes sense.
So it was a probability 2 point.
It makes sense. I just was expecting to get exactly the same numbers, and I was taken aback.
Yeah, no, that's cool. So I just want to take a look and see how far off that is. It's a good point, and I'll say something about that in a second. So here I'm sharing my R. I just did the calculation of what should lambda be, and I used 1.75. But if you use Patrick's and throw that in there and compare that prediction with the original binomial prediction, yeah, it is better. Okay. So the point I want to make here that Patrick is bringing up is rounding matters. Okay, rounding matters. Don't round unless you absolutely need to. And if you're using R, you don't need to round. Okay. If you're using R, never round. Let R do the rounding. It'll do it in the background. And it does calculations that carry out these numbers to more decimal places, I'm sure. As soon as you round, you start introducing error. And that makes you a bad person, right? We want to see what the statistics say. Don't introduce unnecessary variation into the calculations we're making by rounding things. So my using 1.75 instead of 1.755656, that made me a bad person for a moment, and so now I'm fessing up. But this is a good lesson. It makes a difference. Rounding makes a difference. Don't do it unless you have to. If you're computing things by hand, by all means round, because when you're computing things by hand, you're trying to get an idea of what the number should end up being. But when we're using a computer, just let it do all the heavy lifting. That's why we're using them in the course. All right, let's do, this is a cool one. Continuing with the cancer theme. let's talk about radioactive decay. And you might recognize the name Geiger. I don't know the guy's first name. I think he was German. But in 1910, he and this other guy named Rutherford did an experiment where they were trying to understand the dynamics of radioactive decay. And they were interested in how radioactive materials would emit alpha particles. And alpha particles are radioactive particles that are, pretty, well, I'm not a physicist. They're not very dangerous to us. I think they get absorbed by our skin. They're not a big deal. So they created an experiment where they took some polonium, which emits alpha particles, and they set up a little screen that allowed them to detect collisions with these alpha particles. So the polonium and the screen were set up in such a way that if the polonium emitted an alpha particle in a direction, they could see it and they could count it. So they could count these emissions of alpha particles. And what they did is that they ran an experiment, and in periods that were as long as, or that were exactly 1/8 of a minute long, they counted the number of alpha particle emissions. Okay, and so they did this many times, and they recorded the number of counts in each of these 1/8 minute periods. And so let's model emissions of alpha particles. And I'm going to show they're well modeled. No, there's no hyphen there. By a Poisson distribution. Okay, so we're going to show that a Poisson distribution is a good predictor of alpha particle emissions. That is to say, a radioactive substance emits or decays, undergoes radioactive decay in a very random way. And that randomness can be approximated by a Poisson distribution. And Geiger and Rutherford showed this. So let me go back to R. It turns out somebody put this into R. We can access this data right through R. So I'm going to install a package called VGAM. Oh, well, I can't do that by command. So do it through the menu. Oh, I missed an S. So install packages. So I'm having R install this package VGAM. And then I'm going to load the package into my instance of R that I'm running right now. And it's loading a couple other packages that it needs to load. And I'm going to type in Rouge. And so this is a data set that comes with VGAM. And Rouge stands for Rutherford, RU, and Geiger, GE. So this is the data set that they collected through their experiment with the polonium and the little screen. So there's 2 columns here. You're seeing 3, but this leftmost column is just a numbering column, or a numbering column. So you can see there are 15 rows So don't be distracted by that. Focus on these other columns. This first column is called counts, and the second column is called number. I believe this rouge here. So I just executed a command called structure, and I asked, what's the structure of rouge? And R tells me it's a data frame. So this table we're looking at here, it's called a data frame. It's got 15 observations, that is 15 rows, and 2 variables, right? 1 variable for each column. And then here, R tells me one of the variables is called counts, and one of the variables is called number, and it lists those. So if I wanted to work with one of those variables, I could say rouge and then put a $ and say counts. And it would show me that vector of all the counts. So it shows me this column right here. I'm running my mouse up and down it. And if I wanted to look at the total number of counts, I could say sum the variable rouge counts. And it gives me 2,608 observations. Okay. So let's look up at this table again. Each one of these rows corresponds to the number of alpha particles that intersected that screen during a single 1/8 minute period, a 1/8 minute event. So 57 times there was no alpha particle, 203 times there was 1 alpha particle, and so on and so forth. Once there were 14 particles, you get the idea. So in the language that we've developed in this course so far, this is like a frequency table. And I could make a bar chart of this. Maybe I'm not going to try because I don't know what that is off the top of my head. I'd have to look at a reference. We could make a bar chart to look at a frequency plot. So with that in mind, I could do this. I'm going to make a new variable. I'm going to say let rouge, and I'm going to say frequency. So I'm making a new variable, and I'm going to say let that be equal to rouge counts over the total number of observations that were made that we already figured out was 2,608. And so now when I ask to look at the rouge data frame again, you'll see it's added a column called frequency, right? And so we can think of this actually as a probability. What's the probability that if I did this experiment again, I'd only see 1 alpha particle in a 1/8 minute event? Okay. So what am I trying to do? Oh, I'm trying to show that these counts are well modeled by a Poisson random variable. So for a Poisson random variable, I need to find a lambda. Okay, so let me go back to my iPad. So if we say x equals the number of alpha particles emitted during a 1/8 of a minute event, my claim is x is a random variable that's distributed as a Poisson lambda random variable. But now the question is, what's that lambda? And you'll recall lambda is the expected value or the average number of events. I'm sorry that I'm low again. Okay, so for a Poisson random variable, lambda, you interpret that as the expected value of the random variable, or the expected number of particles we expect to hit the screen during a 1/8 minute event. So I need to, for me to work with the lambda that works for this modeling, I need to go and figure out what's the expected value of the number of alpha particles. So what we're going to do is we want to calculate the expected value of the observations. So that's going to be the weighted average of the number of alpha particles times the frequency of that count. I'm sorry that's hard to read. Okay. That is, we're using the idea that an expected value is the outcome times the probability of that outcome, and you sum over all the outcomes. And in this case, our outcomes, omega, are zero alpha particles, 1 alpha particle, 2, all the way up to, I think it had as many as 14 alpha particles. So we're going to go back to R in a second. But these X's here, these represent the variable rouge count or counts. And the probabilities here, these are the values of that new column I made, the frequency column. And so I want to add up the products of these things. So I'll write down on my iPad how I'll do that, and then I'll type it in. So the way we do that in R is that we write the two vectors and we multiply them like this. And for R, this is a term by term product. So in R, if you took a vector AB and you multiplied it by a vector XY, for R, that would give you AX comma BY. So that's term by term multiplication. And then what we're going to do is we're going to sum over all of those. So that will give us the expected value. So let's go do that. So we've got counts here. We've got frequency. No, the number is what we want. We've got the number here and we've got the frequency. So I got that wrong in my notes. We'll go back and fix that. So I want to sum over rouge number times rouge frequency. And this is going to give me my expected value. So there we go. That's my lambda. There's another way you can do this in R. If you like to functions and you like to trust software, there's a function called weighted mean. So I'm going to look at the help. Oh, come on. So here's the help page for weighted mean. So the function syntax is weighted.mean, and then you put in a bunch of vectors. And so X and W, X is the object containing the values whose weighted mean is to be computed. So for us, that's the number of alpha particles. And then W is the weights. For us, that's the frequency. So I could type weighted mean of rouge number, comma, rouge frequency. Yep. Those are bad. We get exactly the same thing. So that's our lambda. So let's go back to the iPad. And I just crossed out counts and put a number because that was an error. So R tells us our lambda is, I'll go back and grab it, 3.871549. Okay. And in actuality, this is an approximation, but I'm just going to write it as an equality. Okay. So our claim is that these alpha particles are emitted in a pattern that's well described by a Poisson random variable with lambda. Oops. Equal to that. So how can we test that? Well, we'll ask, what's the probability? Well, let's see here. Let y be the experiment of running 2,608 let's run 2,608 experiments of Rutherford and Geiger. Right. And now let's ask, what's the probability that if I do that, I get K alpha particles. So if I'm using the exponential, I'm sorry, the Poisson random variable, this is going to be equal to the Poisson. Well, let's just write it down. E to the minus lambda times lambda to the K all over K factorial. That's the formula for a Poisson random variable. So I need to calculate these for each of the Ks. R has a way of doing this. D Poisson K lambda. That's how you calculate that for a Poisson random variable. So what we want to do, oh no, wait a second. This is not exactly correct. This is the probability that it happens for one event. We want to do 2,608. So I need to multiply this by 2,608. Okay. So this is going to be the number of alpha particles we expect to see. After 2,608, 1/8 of a minute events. Okay, so let's calculate that. So what I'm going to do in R, I'm going to take a vector V and let it be the possible number of alpha particles we expect to see, or at least that Rutherford and Geiger saw. And then I'm going to let Y be the value of the Poisson probability mass function at V with the lambda that we calculated. Nope, that's not quite what we calculated. 549. Okay, so let's go to R and do that. So I'm going to say V R is the vector of number of observations, 0 to 14, and Y is going to be 2,608 times the value of the Poisson probability mass function at our observations with lambda 3.871549. Right. R does a calculation really fast. Let's look at the vector. Hey, there are a bunch of numbers. But I'd really like to see these numbers in context up here. So what I'm going to do is I'm going to make a new variable called Rouge Predicted. And I'm going to assign its values to be those that I just calculated. And so now when I go and look at my data frame, I have my new column here, this fourth column, and you can look at the predicted number of times we see 0 alpha particles. We predict, or the Poisson random variable predicts 54, and Rutherford and Geiger saw 57. So you can go down the column and see what the predictions are and how they compare with Geiger and Rutherford. And they're pretty close. That's not too bad. And in fact, historically, people looked at this and said, holy crap, that's good. So we're going to say the same thing. But it would be nice if we could have some sort of objective measure of how good it is. And this is one of the problems that we see in popular media when people are talking about numbers and they're talking about comparisons. They're very sloppy about it. They talk about percentage increases in the number of COVID cases or the absolute number of increase in COVID cases, for example. And oftentimes the way they choose to talk about that is misleading. So how can we make a reasonable comparison that can be used in all kinds of situations and is easy to interpret? So one standard way of measuring accuracy is to look at the difference between the values. So what's the difference between the real count that Rutherford and Geiger saw and our predicted count? So that would give you an absolute error, right? So in this case, our absolute error is just a little bit under 3. But we want to take into account the size. What was the size of our prediction? Because if we were predicting 1 and our error was 3, that would be a huge error. But if we were predicting 1,000,000 and our error was 3, we want to think of that as a tiny error. So what we'll do is we'll look at the difference between the actual counts, the observed counts, and our predicted counts, and we're going to divide that by our prediction. So I'm going to write that down in R here. So I'm going to make a new variable, Rouge, called accuracy. And I'm going to define it as, and let's say it's going to be Rouge predicted minus Rouge counts, all divided by Rouge predicted. Oh, it didn't like something. Oh, a typo. All right, I like that. So now if we look at the table again, I've got an accuracy column here. And the way I defined accuracy, if my prediction was higher than the observed value, my accuracy is going to be a positive number. If it was lower, my accuracy is going to be a negative number. So you can see here, just from looking at the signs, if I was an overestimate or underestimate. And then your accuracy is a percentage. So for the first observation or the first number of 0, we had a 5% error. 5% relative error is what we would call it. For the second observation or for one observation, we had a 3% relative error. And so these errors are really pretty small. And as you get down here to the smaller and smaller number of observations, the error gets bigger and bigger. But that's to be expected because the number of observations is pretty small. So it's easy to get a big relative error. But this is a standard way in statistics of measuring the error of a prediction, is using the idea of relative error, right? So this is the error relative to your prediction. You could just as well have put the number of counts, the number of observation down here. And so that would be error relative to the observations. And as long as you're consistent, this measurement of accuracy is legit and it communicates pretty clearly. So let's do one more example. I think we've got time for one more example. Going back to the iPad. So let's talk about nuclear power. There's a theme today. So nuclear power is generated through nuclear fission. I think that's what it's called. And that's where you take a radioactive mass and you put it on next to another radioactive mass. And as those masses decay, they fire radioactive particles to one another, which causes more decay. And the firing there creates heat. And that heat is used to heat up water, and that hot water boils and generates steam, and the steam turns turbines, and turbines generate electricity. Nuclear fission. The problem is, if you're not careful, those radioactive masses, the way they interact with one another, that can go out of control, and the heat can skyrocket, and you can get what's called a meltdown. And HBO had a great documentary docudrama about the Chernobyl nuclear disaster in the Ukraine. Beautiful, beautiful piece of art. There was a meltdown. So meltdowns are bad. So to avoid meltdowns, nuclear reactors have what are called control rods. And what the reactor does, or the reactor operators do, is if the nuclear mass is getting too hot, they'll lower into the reaction chamber these control rods, and those control rods absorb the particles emitted by the nuclear mass. All right, so they absorb the neutrons and slow the reaction in the chamber. Okay, so by raising and lowering these control rods out of the nuclear container, you can speed up or slow down the reaction. If you are headed toward a meltdown, the idea is to put a bunch of rods into the vessel to absorb as much of those neutrons as possible and slow that reaction and bring it back into a safe level. So suppose a reactor has 10 control rods. Now, reactors generally have on the order of hundreds of control rods, but just for the sake of an example, we're going to say there's 10. And each rod has an 80% chance of working correctly in a pre-meltdown situation. Meaning that if an operator thinks there's a chance of a meltdown and starts lowering rods, each rod has an 80% chance of working at that time. For the rods to prevent a meltdown, at least 50% of them need to function correctly. So in this case, you at least need 5 to go into the container if you expect the meltdown to be controlled. What's the probability that if a meltdown starts, the control rod system fails? So let's calculate that probability. So I'll show you that we'll use a binomial probability distribution to model this. First, I'm going to start with the idea of a single rod. So a single rod is like a Bernoulli event with probability 80%. Single rod working correctly. So if you put 10 rods together, then we're getting a repeated trial with 10 rods, and that's a binomial experiment with n equals 10, and each of those Bernoulli trials having an 80% chance of succeeding. So this is the binomial, this is the distribution we'll use. And so we want to know what's the probability of failure. And we know controlling a meltdown succeeds if 50% of the rods are put into the control chamber or in the reaction chamber. So we want to know what's the probability that fewer than 50% is going to work. So what's the probability that if we try to put all the rods in, we're only able to put in 4 or fewer? So I guess it would be good for me to have written something up here. It's a little clearer. Y is the number of control rods that work at a meltdown. Okay, so with that definition of the random variable Y, it's clear that we want to know what's the probability that the number of rods that work are 4 or fewer. And then thinking of this process as a multiple Bernoulli trials, we can see that Y is a binomial. Okay, so let's use R to do it. So we're going to calculate what's the probability if Y goes from 0 to 4, where n is 10, and the probability of success is 0.8. So we're going to sum over those and see what we get. All right, so let me share R, and we'll do that together. So let's sum the values of the binomial probability mass function. It takes on the values from 0 to 4, where there's 10 trials, each with a probability of 0.8 of success. Hit return, and I get 0.6%. So according to R, let me go back to the iPad. According to R, our sum here is approximately 0.006369382. So there's about a 6% chance of failure. No, 0.6% chance of failure. So that's pretty reassuring. Okay. And so that's how we would use a probability distribution to answer this question in this case. Could I use an exponential function to do the same thing? Anybody want to hazard a guess?
Do you mean Poisson?
Oh, yeah. Yes, I mean Poisson. Could I use a Poisson to model this process?
Yes, you could. You would replace d binom with d plus, and you would replace the 0.8 with, sorry, the 10 and the 0.8 with 10 times 0.8.
Yeah. All right. I'm just noticing we're over time, so I'm sorry that I lost track of time. So Patrick, you're right. You could do that, but it wouldn't be a good idea because your n is so small. a Poisson approximates a binomial only when that n is really, really big, and then the product of those two numbers isn't a humongous number itself. So you just have to be careful. Yeah, you could use an exponential, but your approximation is going to be really bad. It's not a wise choice. Okay. Again, sorry I went over. I understand some people had to drop off earlier because of that, but I'll leave it there and watch for homework. Hopefully this was good for those of you who asked for some examples. I tries to choose some that I thought were valuable, and I will see you in class on Tuesday.
Thank you, Dr. Miller. Have a good weekend.
Thanks. You too, Ashley.
Bye.
Bye, Lolly.
When you said it was bad, you weren't kidding. It's like it gives 9.9%. That's a terrible approximation.
Yeah, it's like 50% off, right? Oh, it gives 9.9%?
Yep.
Oh, that's humongous. That's like 1,000% off. Yeah. But it's a good question. Can you use an exponential? And you can always try and see, but it's a bad idea because of that size of n.
Also, why are we using D binom rather than P binom? P binom will do that sum for us, and I would assume it would be more accurate.
It's gonna be this. It's gonna be exactly the same. I'm choosing to stick with one function right now for people who are new to coding, and we can explore some other ones. So feel free to use the P binom. I mean, it's going to give you the same answer. You just have to make sure you use the parameters correctly.
Okay, thanks. See you.
See you, Patrick. You good, Kevin? Saul?